Welcome to the lesson video for section 5.3. Today we're going to be learning about how to solve polynomial equations, and our objectives are that we can solve polynomial equations by factoring as well as by graphing. So to begin, let's talk about how to solve an equation by factoring. First thing we want to do is write the equation in the form p of x equals 0, which means we set the polynomial equal to 0, and p just stands for some polynomial function. After that, we want to factor p of x by using the various methods we have learned in the past, as well as one new one I'm about to teach you in a second. Once you factor, you want to use the zero product property to find the roots, which means you set each of the factors equal to 0 and solve for the variable. Here in example 1, we are given a few polynomials. We need to figure out the real or imaginary solutions of each. The first thing that I notice in part A is that the polynomial given is not in standard form. So that's the first thing I want to do, is make sure it is in standard form and it's equal to 0. So I want to subtract 3x to the other side. So that means I have 2x to the third minus 5x squared minus 3x equals 0. Next, I notice that there is a GCF among all of the terms, and I notice that it is x. So as always, we factor out the x, or the GCF, in common. So then we get 2x squared minus 5x minus 3 equals 0. And we learned how to factor this expression inside the parentheses last chapter. When factoring a quadratic with a leading coefficient that is not 1, in this case we have 2 in front, we want to use a method where we take the a value, which is 2 in this case, and multiply by the c, which is negative 3 in this case. So I'm taking 2 and negative 3 and multiplying, and I get negative 6, so that goes up top of the x, and then the middle term is negative 5, that goes on the bottom. What two numbers multiply to give me negative 6 but add to give me negative 5? And that should be negative 6 and 1. So then now we write this as 2x squared minus 6x plus 1x minus 3. The GCF is just staying out in front the whole time. We're using factoring by grouping inside. So we have a GCF for the first two terms. We have 2x. So then we get x minus 3. And then the GCF for the last two terms is just 1, so plus 1. X minus 3, and in the factoring by grouping process we always get the same thing inside the parentheses, which we do have that in this case. So then we factor out what's in common, x minus 3, and then what's left is in front of those two terms, so 2x and plus 1. So 2x plus 1 comes down, and the GCF of x is still in front. So that is our factored form. Now what we want to do is set each of those factors equal to 0 using the zero product property. When solving for x in each of those expressions, I get x equals 0, or x equals negative 1/2, or x equals 3. So that means those are the solutions. As always, we could check our answers by plugging each of those solutions back in for the original equation separately, and we would find out that it would make the equation true. In part B, we are given another polynomial where we do not have it in standard form yet, so the first thing I want to do is put it in standard form and get 0 on one side of the equation. So I'm subtracting 6x to the third from both sides. So make sure you paste that in right after the 3x to the fourth, because standard form means we have biggest exponent to smallest. So now we have it in standard form. When taking a look at the terms in this polynomial, I notice that 3x squared is the GCF, so I'm going to be factoring that out in front. And then when I factor that out, I have x squared minus 2x plus 4 remaining. So that is my factored form. From there, I'm going to set each of those equal to 0. And I know that I cannot factor that quadratic inside the parentheses because I did the x and I have 4 and negative 2 there, and there is no pair of numbers that can multiply to give you 4 but add to give you negative 2, so that means we're going to be using the quadratic formula in a moment. So I'm setting each of these equal to 0. The first factor is pretty easy to solve for because we can just divide by 3 and we still get x squared equals 0. Because both equations have 0 as a solution, the solution has a multiplicity of 2, which we talked about in a previous video. Now for the next part, I'm going to be using the quadratic formula. So I'm labeling my ABCs, and I'm going to be using that form now. So I have minus b, so positive 2 because it's double negative, plus or minus the square root of b squared, which is negative 2 squared, minus 4 times 1 times c, which is 4, all over 2 times 1. When simplifying the operations under the radical, I get negative 12. So that means we have 2 plus or minus the square root of negative 12 over 2. We learned in the last chapter, specifically section 4.8, how to work with radicals that have a negative number underneath. And we're going to be using the imaginary unit I to assist us. So remember, we can simplify this as 2 plus or minus the square root of negative 1 times the square root of 4 times the square root of 3. So square root of negative 1 is I. Square root of 4 is 2, and we cannot reduce the square root of 3, so that remains. So we have 2 plus or minus 2i times the square root of 3 all over 2, and then dividing both of those terms by 2, we get 1 plus or minus I square root of 3. So that means our solutions are 0, 1 plus I squared root of 3, and 1 minus I squared root of 3. So that means that original polynomial had both real solutions as well as imaginary solutions. This key concept summary box is going to be really helpful in organizing the different techniques that we have available to us. And several of these we have used in the past, specifically in Chapter 4. So the first one is factoring out the GCF. So what you want to do whenever you're given a polynomial is, first of all, check to see if there's a GCF, anything in common that you could factor out. In the example that we're given, we notice that 5x squared is a GCF, so that's what we factor out. Whatever is remaining is what you divide by 5x squared. So the original polynomial divided by 5x squared gives us a remainder of 3x squared minus 4x plus 7. So that's what's inside the parentheses. The second technique is quadratic trinomials, which we worked with last chapter. And when we have a leading coefficient besides 1, in this case we have 6 in front, we always took that first number, we multiplied by the last number. That helped us figure out what to work with, what numbers in the x, and then from there, what numbers can we split up the 11x into. So we would split it up into 15x minus 4x, and then from there we would use the factoring by grouping process that we're going to talk about in a moment. The next technique is the perfect square trinomials, and that's when the first term and the last term are both perfect squares. So you can see those shortcuts right there. Difference of squares, that's another shortcut that we used last chapter. And that's when we have a perfect square in front, a perfect square in the back, a minus sign in the middle, and the middle term is actually missing. So that means we have, in factored form, it would just be the same term in front for both parentheses, the same term in back for both parentheses, and then a plus or a minus. Factoring by grouping is the same kind of thing that we did up here, where we group the first two terms, we find the GCF, we group the last two terms, we find the GCF, and then we factor out that term that's in common, the x plus 2 in this case, and then whatever's left is what's in front, so x squared and minus 3 drop. So that would be the factored form by using grouping. The method of sum or difference of cubes is new to us, so let's take a moment to talk about what it is. So I know I'm going to be using the sum of cubes technique here in the first example on the left side because the first and last term are both perfect cubes. So that means you can take the cube root of each term and you will get a nice expression. So let's take the cube root of 8x to the third. So what number do we have to multiply by itself 3 times total to get 8x to the third? That would be 2x. And then what do I have to multiply 3 times by itself to get 1? Well, that's just 1. So now that I know that 2x cubed is 8x cubed and 1 cubed is just 1, and there's a plus sign in the middle, I can identify this term as a and this term as b, and that's just the terms inside the parentheses. So to put this in factored form, I'm going to take my a, which is 2x, and my b, which is 1. So I have a plus b, or 2x plus 1, in the first set of parentheses. And then the second set of parentheses, I have a squared. Well, a squared, or 2x squared, quantity squared, is 4x squared. In my last space, I'm going to take my b and square it. Well, 1 squared is just 1. The minus sign is built in, so make sure you put a minus, and then you multiply the a and the b. In this case, we have 2x and 1, and when you multiply that, you just get 2x. So the factored form of 8x cubed plus 1 is the quantity 2x plus 1 times the quantity 4x squared minus 2x plus 1. When dealing with the difference of cubes, the process is very similar. The only difference is where the negative sign is located. So taking a look at this one, we have the same numbers. The only difference is the minus sign in the middle instead of the plus sign. So I'm still taking the cube root of each of those terms, so I still get 2x to the third and 1 to the third. Now taking those a and b values, I'm just going to have 2x minus 1 in the first set of parentheses. And then from there, I'm going to have 4x squared plus 2x plus 1. So the only difference between the sum of the cubes and the difference of the cubes is where the negative sign is located. In the sum of the cubes, there's a plus sign in the middle because it's talking about the sum. And then in the second set of parentheses, there's a minus. And then for difference of cubes, it's the exact opposite. So there's a minus sign in the first set of parentheses and then a plus sign in the second set of parentheses. Before we do example 2, I just want to show you the most common perfect cubes that we will see, and I think it will be helpful for you to write down this list. In example 2, we're going to be solving a few polynomial equations by using the factoring techniques we just discussed. So in example A, we have x to the fourth minus 3x squared equals 4. The first thing I notice is it's not in standard form, and we don't have a 0 on the right side, so that's the first thing I do is I take care of that by subtracting 4. So that means I have x to the fourth minus 3x squared minus 4 equals 0. I notice that there's no GCF, so I can't factor anything out there. And I also notice that there is not a quadratic here. So the first thing I'm going to do is by using substitution, I can then make it into quadratic form and factor from there. So in this case, I'm going to be letting a equal x squared. So that means I now have a squared minus 3a minus 4 equals 0. So taking a look at this think box over on the left side, when you substitute a for x squared, we now get this quadratic that we can factor. You may be thinking to yourself, how do I know if I can factor a quadratic? Well, we did talk about this briefly last chapter, and let me remind you now that you can always calculate the discriminant, which is b squared minus 4ac. If that discriminant is equal to a perfect square, that means you can factor that quadratic. And if we were to do that, we would find out that it is equal to a perfect square, so that means we can use the x method to factor. So setting up the x on the side, the numbers that work are negative 4 and 1. So now we can write a minus 4 and a plus 1. And that would be the factored form. Now we can replace a with x squared. So we really just use that substitution to assist us in the factoring process, and then from there we're putting x squared back where it is. We have two expressions multiplying to give us 0, so that means we want to factor if possible and then set each of those factors equal to 0. When I looked at x squared minus 4, I thought to myself, oh, that's the difference of two perfect squares. We learned that last unit. So we can actually factor that by doing x plus 2 times x minus 2. The second expression, x squared plus 1, cannot be factored because it's not the difference of two perfect squares. It's actually the sum. And if you can recall, in that case, we will need to be using the imaginary unit I to assist us in that factoring process. Setting each of those factors equal to 0, I get x equals negative 2, x equals positive 2, and the last one we need to isolate the x. So I'm going to subtract 1 from both sides, so I get x squared equals negative 1. Take the square root of both sides, so I get x equals positive or negative square root of negative 1, and we know from last chapter that the square root of negative 1 is I, so that means I'm getting positive or negative I. So the solutions are negative 2, positive 2, I, and negative I. So the first two roots are the real roots, and the last two roots are the imaginary roots. We can use our graphing calculator to help us check our answer. So I used my graphing calculator. I typed in the equation y equals x to the fourth minus 3x squared minus 4, which was my standard form of the original. And then you can see in this graph that the graph shows zeros at x equals positive 2 and x equals negative 2. It also shows 3 turning points here, here, and here, and that tells us that there are imaginary roots which are not appearing on the graph. In part B, we're given the equation x cubed equals 1. So the first thing I would like to do is get it in standard form and set it equal to 0. So that means I'm subtracting 1 from both sides, so I get x cubed minus 1 equals 0. Taking a look at this, I know that this is the difference of cubes, so I'm going to be using that shortcut factoring process we talked about a couple minutes ago. So in this particular case, our a value is x and our b value is 1. So factoring this, I'm going to have x minus 1 in the first set of parentheses, a minus b. And then I'm going to have a squared, which is x, so x squared, plus a times b is just 1x, and then b squared is just 1, because 1 squared is just 1. So that's our factored form. Now I'm going to be using the zero product property to set each of these factors equal to 0. So that means I have x minus 1 equals 0, add 1 to both sides, and we get x equals 1 for our first solution. And then we want to do x squared plus 1x plus 1 equals 0. And taking a look at that, I won't be able to use the x method because there are no numbers that multiply to give you 1 but add to give you 1 at the same time. So that means I'm going to be using the quadratic formula to assist us in finding these zeros. I just took a moment and plugged in my ABCs for the quadratic formula, and now I'm going to reduce what's inside the radical. So we have x equals negative 1 plus or minus the square root of negative 3 over 2. And I see that I have a negative under the radical, so that means we're going to be using I. So I have negative 1 plus or minus I squared of 3 over 2. So that includes our two zeros that are imaginary. So that means the solutions of the original equation x to the third equals 1 are positive 1, negative 1/2 plus I squared of 3 over 2, and negative 1/2 minus I squared of 3 over 2. So those are the three solutions. The first one is a real solution, and the last two are imaginary solutions. We are also going to be able to find our real roots by using our graphing calculator. So that's the process we're about to go through right now. So in example 3, we're given the equation x cubed plus 5 equals 4x squared plus x. The first method that we're going to go through is graphing each of these equations separately, as in using a system of equations, and then using the intersect feature to figure out where they cross. So to find the x values of the points of intersection. So pull out your graphing calculator and go to the y equals and take a moment and type in both of these equations. So now that I have these two equations inputted, let's go to the trace feature, and we can see that the two curves are intersecting in 2 points. The first point will be easier to get. So let's go to second calc and then to intersect. We've used this before. So choose the first curve and just choose a point close to the intersection point, and now it's jumping to the second curve, and choose another point on that curve. And we see that our first intersection point is at the approximate coordinate of negative 1.09 for the x-coordinate. So that's our first solution. Now to get a closer look at the curve in the top right corner, you want to arrow over to that region and then go to zoom in. Enter and enter. So you can see one more intersection point there. So now let's use the intersect feature again. And we get our second intersection point of approximately 1.16. For my last intersection point, I had to adjust my window to find it. So you can feel free to use the same increments and the min and max values if you'd like. So now going to trace, I am going to use the intersect button again. And it's on the first curve, enter, second curve, enter, and lastly, it finds the remaining intersection point. The x-coordinate is approximately 3.93. So using the first method of graphing each side of the equation separately and finding the intersection points, we got the approximate solutions of negative 1.09, positive 1.16, and positive 3.93. The second method that we will be working through is using the original form and putting it in standard form, which I showed you right here, to get a polynomial of x cubed minus 4x squared minus x plus 5 equals 0, graphing that function and then finding the zeros by using the zero feature on the graphing calculator. Take a moment to type in the polynomial that we just talked about, and then go to your window and feel free to use the same constraints that I'm using, negative 5, positive 5 for the x min and max, and then negative 10 and positive 10 for y min and y max. So now going to the trace feature, we see the cubic function, and now we want to use the zero feature 3 times to get our zeros. So left bound, you want to go on the left side, and then right bound, you want to go above. So we get our first zero of negative 1.09. Using that same process, I got another zero at the x-coordinate of 1.16 approximately, and lastly, x equals 3.93. Out of the two methods, I think that this method is a little bit easier and quicker to get the solutions. Because in my opinion, it's easier to adjust the window to make sure we can find all of the zeros on the x-axis versus finding the intersection points, which took a little bit longer. So feel free to use either method. And here's our last example. It's a real-life application problem. It says, close friends Stacy, Una, and Amir were all born on July 4th. Stacy is 1 year younger than Una. Una is 2 years younger than Amir. On July 4th, 2010, their product of their ages was 2,300, more than their sum of their ages. How old was each friend on that day? So as with any word problem, you always want to define your variables that you'll be using. And since all of the ages are related by Una, or comparing to Una's age, we're going to be saying X is Una's age on July 4th, 2010. So because Stacy is 1 year younger than Una, that means Stacy's age is going to be X minus 1. And since Una is 2 years younger than Amir, Amir's age is going to be X plus 2 because that means he's 2 years older than Una. The word problem said that the product of their ages was 2,300 more than the sum of their ages. So I just wrote that in word form. Product of ages equals sum of ages plus 2,300. Now we're going to take a moment and substitute in the expressions we just defined above. So get this equation here. Now we need to multiply the two binomials using FOIL. So when I do that, I get x squared plus 1x minus 2, and then we want to distribute the x to each of those terms inside the parentheses. When distributing the x to each term inside the parentheses, I get x cubed plus x squared minus 2x. On the right side, I'm going to combine like terms by adding. So we have 3x and then plus 2,301. And I'll drop that down one more time. And now we want to get it in standard form, which means we want to get all the like terms on the left side and set it equal to 0. When doing opposite operations, I get a polynomial of x cubed plus x squared minus 5x minus 2,301 equals 0. We're going to graph this to figure out the zeros. I just typed in this polynomial into my y equals, and now I also spent a couple minutes testing out different window values to make sure I could find the x-intercept. So go to your window feature now, and then you can copy the x-min, x-max, y-min, y-max that I chose. And like we've talked about in the past, this is kind of like a trial and error. You want to make sure you have what you're looking for inside your window. So now let's go to trace. You can see the curve, and at the very top we have the x-axis. So now let's use our 0 feature that we've used in the past. You want to choose, for the left bound, you just want to choose 1 point below the x-axis, and then for the right bound, you want to choose 1 point above the x-axis. So I have one of each now, and I find out that my 0 occurs at the coordinate 13, 0. Since real solutions only make sense in this particular case, we don't need to worry about imaginary solutions. So that means x equals 13. And remember, Una's age is whatever x is. So that means Una is 13 years old. Now that we know that Una is 13 years old, we subtract 1 from her age to get Stacy's age. So that means Stacy is 12 years old. And for Amir's age, you just need to take Una's age and add 2. So that means Amir is 15 years old. Here are our lesson check problems for this lesson. I am asking you to do all of them so you get maximum practice. Please let me know if you have any questions the next time we meet.